Hello, welcome all with the first Sport talk of the day. Rob Claessens is going to talk about predicting the spring for the cycling, cycling classics. So I'm gonna give it to Rob. Give him a warm applause, please.
Yes, thank you. I guess you can hear me. Last year I attended PyData for the first time, also in Eindhoven, and I got sort of inspired, so I thought let's take a deep dive into this topic, and I applied it on something I love, which is cycling. So now I'm here presenting this. Wait, now this could work. Yeah, so this is content. I hope it's more or less readable. A quick introduction, then yeah, on the setup of my model and how I trained it, an evaluation of the model and some conclusions. First of all, a bit about myself. So I am Rob Claessens. I studied structural design at the Technical University of Eindhoven and then started working at Royal Haskoning DHV, which is a consulting and engineering firm in the Netherlands. Over the years, I sort of evolved into being a software engineer. So I'm involved in automating and standardizing our workflows within the company. And then I need to use this space. So I'm also a proud citizen of Eindhoven, as a few earlier, but I'm not a fan of PSV, which at this point isn't so great because I'm an Ajax supporter. I wouldn't recommend it this year, and also not next year, probably. And then also we got kicked out of the European Championships, so this is a perfect day to not talk about football, but about cycling. Yeah. So what I did is I took a deep dive in neural networks and then applied on cycling. And well, what I thought is let's predict the Spring Classics of cycling for the Scorrido Spring Classics game that I play each year with my friends. What you need to do in this game is select a team of 20 riders with a fictional budget. The riders can be of any team, so it's basically up to you to decide who you want to have. Next, there are 16 Spring Classics in which all of your riders can score points. So basically, if they finish top 20, they'll get points, and those are, of course, added to your own points. And then for each of the races, you select 3 captains, which is very important because they can score additional points. And they basically get this multiplier for their points, so that more or less looks like this, where you see basically your team at the bottom, and then here you see your 3 captains. The first gets his points multiplied by 3 and the last by 2, so also the order of the captains is important. So and then I thought, can I beat myself, but also my friends, if I use the power of AI? And then I thought of a setup for this sort of contest where I play twice with the same team. So I select myself 20 riders. This is what I use in my personal account, but I also make this additional account with the exact same team. But I will, in one account, choose the captains myself, and for the other account, I let a neural network decide which captain to pick. And then, of course, you have this contest, so I had to come up with a name, which is Rob versus Robot. That's for the introduction. So now about setting up my model. So first a bit about data collection. So I took data from ProCycling and Cycling Oracle. ProCycling is the first one, so there you can find a lot of information on basically all riders, but also races in the past and future, which I could retrieve via an API through an open source Python package. And secondly, there is Cycling Oracle, from which I retrieved the rider skill levels. So this is also a platform that does predictions on cycling, and they keep track of the results of riders, and based on that, they compute how good riders are at certain skills. So maybe on hills or mountains, or how good they are at sprinting. So that's what I used for the riders, which I retrieved by some old school copy pasting. So for the rider information, what I took is only the age and weight. For race information, there's more interesting features. So of course, at the left, you see the ranking for this specific race, which was the Ronde van Vlaanderen in 23. The second column, so this one is it says UCE, which is the Cycling Federation. So basically, they assign points for each of the rank a rider finishes. And at the right, you see some race characteristics, which are probably not readable, but the top one is the distance of the race, and then there are a few characteristics that say something about the difficulty of the race. So that's the amount of vertical meters that needs to be climbed, and a score for that specific profile. And lastly, there is a number that is a measure for how strong the competing riders are at the start list of this race. Then a bit more about the form. So what I did is I took results for the last 60 days for all of the riders to compute some kind of form that they currently have. So how good are they in shape for this next race? Let's not do it like this. I plotted this to see what this actually does. So these are 3 riders that are competing in this year. And then you see, for example, the red line is Tadej Pogacar, and then the 3rd classic of the year he won. So you see this jump in his form, of course, which then linearly decays over 60 days. And of course, in all the races they compete, they can score points to increase their form. And that, of course, also includes races like here that are not classics, but of course you can still get points and increase form. And of course, form is a very important factor you can imagine for predicting the results. Lastly, the rider skill level, I took it from Cycling Oracle. So basically they have this large database of all riders, which basically holds information at how good they are at a certain scale. So it is like a flat terrain scale and hills, sprints, etc. And I put this into a JSON file to use for my training. Altogether, that is stored in PyTorch tensors. So each tensor holds 11 rider features and 5 race features, which are used to predict rank ultimately. They're all collected in PyTorch datasets that will be used for training. And for training, I used historical data over 16 classics for 120 riders over the past 5 years, which gave me more or less 2,200 samples. A bit of data processing. I think the usual steps. So I collected all the data and I normalized input and output, after which the samples were randomly divided over training and validation data, each containing 32 batches, and they were stored to further train the model. So of course at the bottom you see some normalized samples. That's all for data processing. Let's look into the more interesting parts, which is model training. Of course, there was quite some trial and error involved because I'm still sort of new to this field. So it took me a while to find a good configuration and also to find the right way of training. But in the end, I had this 3-layered neural network with 16 input features that ultimately predicts one item, which is the expected rank, which is a continuous variable. So I'm not necessarily predicting this integer rank, but just some kind of continuous variable. And I trained for 100 epochs of 32 batches, while I stored, of course, some key metrics during validation loops. And initially I used the R² metric, but later I also included a Spearman's row, which is more appropriate as it is a rank correlation coefficient. And that makes sense for me because I'm not really interested in predicting the exact rank, but I'm more interested in what is the order of the predicted ranks of all my riders. So then rank is important, predicting the exact value is less important. And using this Spearman's row, I reached more or less 0.50 at the right side. So this one, it's sort of, there are quite some amplitudes. So so what I wanted to say there is indeed I could maybe use a smaller learning rate, which could have been better, but I was happy with this outcome, and I could see that there were sensible predictions overall. So this is what I started with. Yeah, so from here on I could predict some races, which at this point became quite easy. So it was more or less automated, this workflow, so I could generate a prediction data loader, which was basically just retrieving all riders from the start list, collecting race data, collecting their rider skills, and putting it all together. I could iterate over this data and predict their rank, and then sort based on this predicted rank, which gives me this. So hopefully it's sort of readable. So here you see a predicted top 10 for Omloop het Nieuwsblad, which is the first spring classic of the year. Wout van Aert is on top. For those that know a bit about cycling, I would say this makes sense. And from this, I could, of course, select my captains for my robot, basically, which is what you see here. So, of course, from my team of 20 riders, I just pick the first 3 that are predicted in my ranking. So for me, that was Wout van Aert, Ties Benoot at the 2nd place, and then Stefan Koen at 5th place. Which gives me this this selection of captains. So is there anyone that knows a bit about cycling? Okay, so from this top 10, who do you think is sort of strange to be in there? What do you guess? Yes, thank you. I'm happy you you got that. So indeed, Jente Biermans is sort of surprising. I would say maybe also Garcia Cortina at 3rd place. I can actually do this. Yeah. So that's also what I thought. So why are these 2 guys 3 and 4 while Arnaud Delis is only ranked 19th? I would say this is a bit strange if you know about cycling, because you would expect them to be the other way around. So Arnaud Delis somewhere top 5 probably. So I then tried to look a bit into my model. And for this I used SHAP values. We saw this morning Lime, but I used SHAP. And with this you can also measure the individual impact of features on your predictions. And what I did is I computed the SHAP values for the top 10 of my riders, which gives this result. So again, you see here the top 10, and then the SHAP values for them, and basically added up per feature, and then ordered based on importance. And what you see is that age is for some reason the most influential factor by far. So twice as important as the 2nd most influential skill, which is hills. So I can imagine that age could be of influence, but maybe not that it would be of this much influence. So yeah, my conclusion was that the relative impact of age is a bit too high to my liking. So at that point I thought I need to fine-tune my model a bit. Which is what I did. So I augmented my training data by shuffling age randomly over all the samples to basically remove any predictive quality of this age in the data. And with this augmented data, I post-trained my model for 20 more epochs with a lower learning rate, which gave me this. So it actually increased my row by 0.15, so that was quite significant. So for some reason, it did train in this direction of making age important, while it was not really beneficial for the prediction. So actually, yeah, this model turns out to be a lot better, I would say, than the previous one. But then, of course, I need to check if this age dependence has been reduced. And the answer is yes. So with the fine-tuned model, I made this graph again. Of course, the top 10 changed a bit because also my model changed. And you see that age, or I hope you can see it, age is still on top. But of course, the relative difference has become a lot smaller. What you can also see is that form, which I think is an important one. It used to be here, and now it's at 3rd place. So form has become more important, while age has become less important, which I think both are beneficial for my model. And then, of course, looking at the top 10, Garcia, Cortina, and Biermans, who were sort of strange to be in there from the start, they vanished at the right side, so that's good. Arnaud Lee skyrocketed from 19 to 2. So also that makes sense because this is actually one of the youngest riders in the peloton. By reducing this age bias, essentially you could end up a lot higher in the ranking. And then lastly, Jan Tratnik also entered the top 10 at 8th place, which is also nice because he actually won a few races before the first spring classic already. So he had good form. So you see that form became more determining, and he actually won this race. So it also gave me a lot more points as I predicted him within the top 10. So yeah, I was quite happy with this. And now I could use this improved model for further predictions. So the old model was used for the first 3 classics, and for the remaining 13 I used the fine-tuned model. So then some evaluation of my model. So I did a bit more with these SHAP values to get a bit of an understanding of my model. Let's start there. This doesn't seem to work well, which is... oh wait, it does, yeah. Okay, so first of all, the 4 races that I took. So of course there are 16 classics, but I took only these 4 to evaluate based on SHAP values, because I think these are representative for the type of classics you would have. So at the left top you see the Scheldeprijs, which is a very flat race for sprinters. And then here it goes more to a bit hilly with some cobbled sections, the gray parts, which are the real classics maybe, so to speak. And then Liège, Bastogne-Liège, which is the most hilly classic, so the most vertical meters. So this goes from flat to more hilly, which is sort of a good representation of the range of classics in the game. Yeah, so it actually works, that's good. So here are all the SHAP values of these 4 races. And again, I took the top 10 for each race and computed the SHAP values for those 10 riders. And this is the absolute value, so it gives a measure about the impact of each feature. Now what you see quite obviously is that form is by far the most influential factor, which I think, to me it makes sense. Good form will probably be a good predictor for future results. So that makes sense, but let's now disregard it to look a bit better into the other features. And separate the rider and race features. So after form, you see that vertical meters is the most influential, second most influential factor. Also here I could see why, because I think vertical meters in a race, so how much do we need to climb, is of course very distinctive, and it will really impact the rank of a rider. That can be expected. So that's the most influential of the form. And then we have age and hills. So these 2. So those are 2 rider characteristics. So again, age we already saw it was quite influential, which is also seen here. And then hills is after that the 3rd dominant factor. To me it also makes sense because being good at hills is quite important for these kind of hilly races. So it makes sense that the model picked this up. And then maybe the last one to discuss this start list. Also there I can see why this is influential. Because of course the type of riders at the start and how good they are, of course, makes a major difference for the rank you would expect from a rider in that race. Let's go to the next one. So, and I also want to take a look into the SHAP values for each of the races, so we can also see how it differs per race, and you can already see there's a major difference. But we're still looking at the absolute values, so let's now take a look at the real values, so you can actually see the difference. So you can see positive and negative values, of course. And then again, from the left to the right, we have our most flat race at the left and the most hilly race at the right. And here it's good to see that when there is a positive SHAP value, this means that this has a positive influence, so to say, on the rank. So that means the rank goes up from 10 to 20 or to 40. So it's actually negative for the rider. If there is a positive SHAP feature, that means a negative impact on the rider's results. And in here you see this, well, at least for the vertical meters, which was the most influential factor, we see that there is this sort of linear arrangement, which goes like this. So it seems that the more vertical meters there are, the more negative the SHAP value is. So apparently that gives a better predicted rank for a race with more vertical meters. And then the second most influential race characteristic was start list, which is this. And again, here you see a linear arrangement, but then opposed. And this actually also made sense. So I looked at the Scheldeprijs, which had the worst start list, so basically not so good riders on the start, while Liège-Bastogne-Liège had the best start list. So indeed, when there is a less good start list, the SHAP becomes negative, so predicted rank for each of the riders will actually get better for them. That's for the race characteristics, sorry. How am I doing with time? Very well. That should be okay. Yeah, so I did the same for the race characteristics, so we can all, rider characteristics. So I splitted them by race, which you can see here. And then of course I'm again interested in the real values, which will give us a bit more insight, hopefully. And of course we saw that hills was an important feature here, so let's try to select these a bit better. It's always tricky when they're yeah, well, you get the picture, right? So it goes again linearly decaying, I would say. And you see again that the most hilly race on the right has the largest negative SHAP value. So at this point, or well, first of all, what we can see here is that apparently a good hill scale gives you a better chance at a good rank for the race. But at this point I was thinking, is there some interaction going on? So the fact that there are more vertical meters, there's a harder race basically, does that impact the importance of the hill scale, and therefore does the SHAP value become more negative? That was my initial assumption, so I thought there's some interaction going on there. But I wasn't sure, because I was also thinking, of course, the top 10 of all of these races differs quite a lot. So maybe these SHAP values are simply a expression of the riders that are attracted to this type of race. Because of course, a race with more vertical meters will attract riders that are better at climbing. What I did to find that out is I took 3 riders that actually won 4 of these races this year, and I predicted only for them, which gave me this result. And then you see that all the SHAP values are the same for each of the races. So the SHAP values are not, well, really useful to find some interactions, at least not used in this way. But yeah, it does give you an idea on what contributions are there, how high they are, and what the direction of the contribution is. So that's for the SHAP values. And next. So then a benchmark comparison. So what I did is I compared my results to Cycling Oracle. It's the platform I already showed you. So they also predict races, and they actually have the scoring system in place. So based on their predicted top 10 and the final ranking of the race, they compute a score, and that is expressed as a percentage of the maximum you could take. And that's what you see here. So at the left, well, we see sort of the legend. So I have, of course, my old robot, which is blue, my fine-tuned robot, which is green, and then Cycling Oracle in orange. And what you see is that the high scores are mostly taken by Cycling Oracle, so these 3. But they also have a few very bad scores. Let's see if I can make that a bit more clear. So Cycling Oracle also had the 2 worst scores of the year. Again, for the cycling followers, this was at Dwars of Vlaanderen with a major crash of Wout van Aert and Mats Pedersen. So this causes the score to go down. And Flash Wallon, it was so cold that only half of the peloton could even finish the race. So also there was some strange stuff going on. Actually, I was able to score a bit better there, so that was good to see. And for Dwars of Vlaanderen, that was because I actually predicted the winner correctly, which was Matteo Jurgensen. So that was fun. But overall, my old model was the worst. Then with I would say significant difference of 4%, my fine-tuned model, but Cycling Oracle still outperformed me by more or less 5%. So they're better, but well, they've been doing it for years. I did it the first time, so I'm sort of happy with it. And then here you see in the next graphic sort of the cumulative scores, and you see that quite consistently. Cycling Oracle is doing better than my robots, but also the fine-tuned robot is doing better than my old one, so not too bad. Maybe lastly, I also looked at my top 10 predicted riders that actually finished top 20, and there you see that, well, by a small margin, my fine-tuned model won. So, well, I need to show that, right? But the differences are quite small, to be honest. Yeah. Well, lastly, how did the contest go? So, my Rob versus Robot contest. Of course, we start off with 0 points, and then from there, after the first weekend, I was ahead of my robot already by quite a margin of almost 12%. That's quite a lot for 2 races, especially thinking we had the exact same team and only different captains. And then, of course, after 3 races, I used my fine-tuned model. Let's see what that does to the standings. So at this point, after half of the races, my robot was actually able to catch up quite a bit. So now the difference is only 2.5%. And then the end score, you see that the robot wasn't able to fully catch up. So it actually lagged behind a bit more at the end. So with a difference of 5%. So conclusion is that I still outscore my robot significantly. These percentages actually are the Scorito scores. So I was better than 65% of the players, while my robot was only better than 49. So that's a significant difference, thinking we have the same team. Also, my friends were better than robot mostly. So, well, I still have some work to do. At least good to see that the fine-tuned model did perform better, like we already saw in the previous slide. Okay, conclusions. Yeah, my model is not yet strong enough to beat well-informed cycling enthusiasts. Well, it was better than like 50%, but it should become even better to rank higher. And I do have this automated workflow, so I can quite easily explore different options, add new features. I could also maybe fine-tune my workflow a bit in getting better data. Remove some features, and I think there's still more to do. So suggestions are welcome. Lastly, understanding and visualizing the model is not easy. That's what I experienced. Especially interactions between features are quite hard to visualize. So also there you can make some suggestion, but at least I learned a lot, and partly from making some very rookie mistakes. But well, that learns the fastest, I think. And hopefully next year I will be back with a robot that actually outperforms at least myself, but also my friends. So that's it. Thank you.
Thank you. Are there any questions?
Thanks a lot for your talk.
Yeah.
I was looking at this model of form you were using, which had this linear decay in it.
Yeah.
If you look at form using body metrics, it most of the time is modeled by an exponential decay. Maybe that would have any influence in your model? What do you think?
I think it could for sure have influence. I didn't really try it, so I just went with linear and saw, well, this more or less works. But it could definitely have an influence because you see that the form sort of increased quite fast for these like Van der Poel, Pogacar, so the real good riders. So of course at the end of the classics, you could see that they were predicted a lot higher than the rest, which also makes sense. But maybe this type of decay that you suggest would be a bit better in sort of counterbalancing that a bit more. Yeah.
Yeah, thanks. Curious what it will bring you next year, because I do agree that the Spring Classic this year was just chaos everywhere. So
So then I did quite well, right? So more than 50%.
I agree.
So I also tried again for the Giro, but then something strange slipped into my model. Maybe also for next year. But I'll keep on improving it for sure. Yeah.
Over there.
Thanks for the talk. Did you think about using betting odds and like betting market, like one to featureize it, and two to see how market would perform in the game?
No. So that's the quick answer. It could be interesting. To be honest, I haven't looked at it, so I was quite busy doing it, and I sort of just finished it in time to use it. But yeah, would be interesting to explore it, to see if I can make some money out of it, right? So.
I'm thinking more from perspective like using betting odds as features too.
As features.
As features, and see how betting odds would run. Like if you use the top three prices, the lowest prices in the game, and how the captain would perform if you use them. Because you score points just for the place you finish on during the race, or you have like some checkpoints.
Yeah, no, it's just for the top 20. So of course, first one gets the most, and there are some team points involved. So that's also something. Yeah, but I didn't fully get how you wanted to include the betting odds. Yeah, let's do it. Yeah.
Yeah, thanks for the talk. As you talked about, there was a lot of chaos. And just like you mentioned, you can use betting odds as well for simulations. So you can like simulate this tournament or this year or competition like 100,000 times. And then you can see how well your model performs compared to your friends or the other model or whatever. Because, I did the same with football. And football and cycling, it's both very random. So just because you have a better model doesn't mean you're going to win when you play once. So that might be good not only to make the model better, but also to evaluate your model.
Yeah, I think I can still learn a bit there. But for the Giro, I actually did it. So I sort of randomly changed form and then ran it like 10 or 100 times to sort of get a view on what would happen then.
Yeah, interesting. Thanks.
Yeah.
Question?
Yeah, thanks for the talk. Just wondering, did you try out other models, like just machine learning, scikit?
Not really. No. So for me, I'm sort of new, so I just went with a neural network. Then later I also saw, could have used another model, like maybe random forest, could have been even more fit for this specific use case. But I didn't really explore it, to be honest. No.
No, I ask because there is another method. It's called learn to rank, and might be ideal for this case, but you might try it.
Yeah. Okay. Thanks.
So I think we can thank Rob for this excellent presentation. And I'm not sure if Yul has something else to.
No, thank you.